All right, chemistry kids, we're here. We're going to do a practice solution stoichiometry problem. Kind of, answer all the types of questions you might have to answer when you mix two aqueous solutions together. So today's lesson is going to focus on formation of a precipitate, and I'll do another lesson here probably coming up over the weekend on the formation of a gas when you have a double replacement formation of gas when you mix two aqueous solutions together. So let's go ahead and jump in to the question. Okay, so again, if you want to pause or write this down, or I'm going to attach this set of notes that I'm going to cover here with the video in Schoology, so you can print them out on your own. Okay, but here's the question we're trying to answer. Okay, so we have a 50 milliliter solution that is 0.75 molar, and it's magnesium hydroxide. So we got a magnesium hydroxide solution. This is the molarity, and that's the volume. And we're going to add it to, we're going to mix it with a 0.75 molar solution of aluminum nitrate, and same volume, 50 milliliters. So we're mixing 50 milliliters of this solution to 50 milliliters of this solution. And what's going to happen is one of the products is going to be insoluble, and you can use your solubility rules to check that out. And it's going to precipitate out of solution. Okay, there are going to be some spectator ions. So after the mixture is mixed together in all of the solid forms, there's still going to be ions dissolved in the water, and two of those ions are going to be spectator ions, and one of the ions that is still dissolved in the water is going to be one of the ions that is precipitating out, but you have extra of. It's going to be the excess ion. Okay, so we're mixing them together, a precipitate's going to form, but we're still going to have ions dissolved in solution, and we want to know what mass of the precipitate is going to form. And this is going to be limiting reactant stoich because we are given two amounts. We're given an amount of this solution and amount of that solution. So we have two amounts, so we got to do two setups. But not only that, we got to identify the ions that aren't precipitating at all. They're the spectator ions. And we also have to figure out what the excess ion is going to be. So I think the best way to do a question like this is to visualize it. Okay, so when we look at this, we're mixing the magnesium hydroxide solution to the aluminum nitrate. So if we visualize the solution, magnesium hydroxide would disassociate like this. This represents one formula unit of it, right? One magnesium ion, but two hydroxide ions, and you draw them separate. That means they're dissolved in water. And if we put some numbers to it, we got 50 milliliters of this solution. The molarity of the magnesium ion would be 0.75, but the molarity of the hydroxide would be double that. Okay, so if we go back up to the question, that said the molarity of this compound in solution was 0.75, but because it's an ionic compound, to get the molarity of the individual ions, you would take the molarity of the ionic compound and you would multiply it by the subscript of the ion. So magnesium is the same molarity, 0.75, but the hydroxide is 0.75 times 2. Okay, and if you notice what we're going to do with the aluminum, that's 0.75 aluminum, but it would be 0.75 times 3 for the nitrate. So you can see we kind of have it written out like this. So we're taking this solution and we're mixing with that solution. And so if we look at the aluminum nitrate solution, for one formula unit of aluminum nitrate, you got one aluminum ion, but you got three nitrates. And we have 50 milliliters of that, okay? And because we have one aluminum for every one aluminum nitrate, the molarity of aluminum is the same as the molarity of the compound. But for the nitrate, it's 3 times the amount, so 0.75 times 3, because we have 3 of these for every one of those, okay? So what's gonna happen when we mix them? Well, we're gonna get a solution that's 100 milliliters, right? 50 plus 50, right? We're gonna get 100 milliliters, but we're also gonna see a precipitate, so that's what these little dots represent, our precipitate. We're gonna use our solubility rules to determine the precipitate, okay? Spoiler alert, it's aluminum hydroxide, but we'll talk about that, okay? So the spectator ions end up being magnesium and nitrate. And again, I'll kind of talk about that when we show the balanced equation. All right, so we got magnesium and nitrate, those are spectator ions. So they're not part of the precipitate, so they're just gonna stay dissolved. The only thing that's changed for them is the volume. Instead of them being in a volume of 50 milliliters, now the volume that they occupy is 100 milliliters, okay? So we have our solid precipitate. We know that that solid precipitate is aluminum and hydroxide ions, okay? So aluminum is precipitating out, and hydroxide is precipitating out. So there will be one more ion we would draw in this beaker, and it just depends on which one we have excess of. So if it turns out aluminum is in excess, we would still have aluminum drawn in here in solution and no hydroxide. But if hydroxide is in excess, then we would have a hydroxide ion here, but no aluminum. Okay, one of these ions is going to end up all the way in the precipitate and have nothing left dissolved. And the other ion you're going to have extra of, so some of it will still be dissolved. Okay. So another way, I think this is a really good way to visualize it. And in AP chemistry, a lot of times they'll have drawings that look like this, with like whether with the correct stoichiometric representation. So like for magnesium and hydroxide, there's 2 hydroxides for every 1 magnesium, and for aluminum nitrate, there's 3 nitrates for every 1 aluminum. So we want to get used to seeing drawings like this, all right? But another way to look at it is to find the net ionic equation. All right, so we have magnesium hydroxide, we have aluminum nitrate. We would expect a double replacement reaction to happen. So we would have aluminum paired up with hydroxide, and we'd have magnesium paired up with nitrate. We need to make sure the ratios are correct. Aluminum is a 3+ ion, hydroxide is a 1- ion, so it's going to be 3-to-1. And magnesium's 2+, nitrate's 1-, so that's going to be 2-to-1. Okay, so notice how over here the subscript of nitrate is 3, but that's because it's paired up with aluminum 3+. But over here the subscript of nitrate is 2, and that's because it's paired up with magnesium 2+. Okay, so if we balance it, we go 3, 2, 2, 3. Okay, now how do we identify the precipitate? This is when you would pull out your solubility rules. Okay, and you would see that nitrates are always soluble, so we would expect magnesium nitrate to stay dissolved. That's why it's still aqueous over here. And so by process of elimination, it's got to be hydroxide. But what you'll read about hydroxide in your solubility rules is that hydroxides are mostly formed in insoluble compounds. So this is going to be our precipitate. That's the solid. Okay. So if we went from here, this is the molecular equation. If we go to the net ionic equation, okay, we'll notice that the magnesium doesn't change. It's dissolved over here. It's dissolved over here. And the nitrate doesn't change. It's dissolved over here and it's dissolved over there. Okay, so the only 2 ions that change are the aluminum ion, dissolved over here, but it's in a solid compound over here, and hydroxide. It's dissolved over here and then it's in a solid compound over here. Okay, so we've identified our spectator ions, and if we go back to the question, remember one of the things we're going to try to figure out is what is the molarity of the spectator ions. Okay. And then if you want the net ionic equation, this would be the net ionic equation, and if you simplify it, 2, 6, 2 simplifies to 1, 3, 1. So aluminum, 1 aluminum ion is pairing up with 3 hydroxide ions to form aluminum hydroxide, and they react in a 3-to-1 ratio there. Okay, so if we run out of aluminum, then we'll have excess hydroxide, but if we run out of hydroxide, then we'll have excess aluminum. Okay. But again, when you're doing the stoichiometry, you can just use the molecular equation. You don't have to use the net ionic equation. So again, that's our precipitate. So let's do our calculations to answer that first question. So again, I'm just going to scroll back up. Okay, our first question, what mass of precipitate is produced? All right, so we come down, all right, and we got our 2 calculations. So this would be figuring out how much precipitate can be produced with the first reactant that I was given. So I was given 50 milliliters, so 0.05 liters, and the molarity was, 0.050 liters, 0.05 liters, and the molarity is 0.75. So if I do liters times molarity, that'll give me moles of magnesium hydroxide. If we go back to the ratio, 2 to 3, right? 2 moles of aluminum hydroxide for every 3 moles of magnesium hydroxide, so 2 over 3. And then 78.01 is the molar mass of aluminum hydroxide. So we do our math. Don't forget to multiply by 2 and divide by 3 here at this step. and we get about 2 grams, 1.95 grams. If we round to 2 sig figs, 2.0 grams, okay? So this is how much precipitate we might get, but that's only assuming we have enough aluminum, right? So this is how much we can get with all of the hydroxide, okay? So let's double check. Let's take our amount of aluminum nitrate, so 0.05 liters times the molarity of the aluminum nitrate, but the mole ratio for aluminum hydroxide to aluminum nitrate is 2 to 2 or 1 to 1, right? 2 moles of this for every 2 moles of that. So you can simplify the ratio, or you can keep it as 2 over 2, same thing. And then times the molar mass. So what we just figured out was, this is the answer there, we have enough aluminum to make 2.9 grams of our precipitate, but we only have enough hydroxide to make around 2 grams of our precipitate. So the answer to the first question, how much precipitate will form, at what mass will form, about 2 grams, 1.95 grams to 2.0 grams, okay? We don't have enough hydroxide to get 2.9, okay? All right, so what have we concluded? We know how much precipitate we're gonna get. We've identified the limiting reactant, hydroxide. Now, if you wanted, you could say magnesium hydroxide, but remember, magnesium is just a spectator, so the limiting, what is truly limiting the reaction is the hydroxide. You run out of it. And aluminum's in excess. So now we can have a final picture of our resulting beaker, right? So we mixed the 2 beakers together. We went 50 milliliters plus 50 milliliters. Now we got 100 milliliters here. And now, because we know aluminum is the excess ion, we got the 2 spectator ions still dissolved, right? And we have some aluminum still dissolved. But notice we didn't draw any hydroxide, and that's because all of the hydroxide ended up in the precipitate, okay? So if you were asked the concentration of hydroxide, you can essentially say it's 0. Now, later on this year, when we get to equilibrium solubility, we'll find out that it's not 0, but it's going to be a lot smaller than any of these molarities. All right, so right now, essentially 0. We'll assume that all of it precipitates out. All right. So remember the next questions. We wanted to figure out the new molarities. So now we're looking at this beaker, our final beaker, where everything's mixed together. We want to find the new molarities of the ions that are still dissolved. So the ions still dissolved are the 2 spectator ions, magnesium and nitrate, and the aluminum ion, which was in excess. So we still have some aluminum dissolved. Okay, and to calculate molarity, it's just moles over liters, right? So we know the volume in liters. 100 milliliters is 0.100 liters. All right, so we have the volume. Okay, and the volume is the same for each of those ions. So the question is, what moles do we have? So we need moles of magnesium, and if we divide by liters, that'll give us the molarity of magnesium. If we figure out moles of nitrate, divide by the volume, that'll give us molarity of nitrate, and the same thing for aluminum, okay? So when figuring out the molarity of the spectator ions, that's a pretty easy calculation. And the reason that is because all the moles you started with that were dissolved, all the particles of magnesium that were dissolved in the beginning, before you mixed the 2 solutions, is equal to the amount of magnesium that's dissolved at the end. So none of it precipitated out. And the same thing with the nitrate. None of the nitrate precipitated out. So all the nitrate you started with is equal to the amount of nitrate you finished with, okay? So you have, all you need to do is figure out how many moles of magnesium you started with, and then divide by the volume, because the amount of magnesium you started with is the amount of magnesium you finished with, right? So there's 2 ways to do this. Let's do the stoichiometric way, all right? So our source of magnesium was magnesium hydroxide. So if we do liters times molarity of magnesium hydroxide, that gives us moles of magnesium hydroxide. And then it's a 1-to-1 ratio. There's the subscript for magnesium is 1. So 1 mole of magnesium for every 1 mole of magnesium hydroxide. So that'll give us how many moles of magnesium we started with in our 50 milliliter beaker. And for magnesium, that's the amount we finished with. So now all we have to do is divide by the volume, the new volume in liters, and that'll give us our molarity of magnesium, okay? We'll do the same thing for the nitrate, but this one we gotta be a little bit more careful because the subscript for nitrate in our source of nitrate was 3. So our subscript for magnesium in our source of magnesium was 1. And so that was just a 1-to-1 ratio. But notice here, to figure out how many moles of nitrate I started with, I would do liters times molarity, just like I did up here. But that's moles of the entire solute, which is aluminum nitrate. But I want moles of just nitrate. So I have to recognize there's 3 moles of nitrate for every 1 mole of aluminum nitrate. So I do the math there, and that gives me moles of nitrate that I started with. And because it was a spectator ion, that's how many moles I finished with, okay? And then I divide by the volume, okay? So the other way to do it, and this works just for spectator ions, is essentially all we're doing is diluting the concentration of the spectator ions. We're increasing, the moles are staying the same, the moles dissolved are staying the same, but you're increasing the volume of the solvent. So when you do that, that's dilution. So because the moles stay the same for the spectator ions, you can use M1V1 equals M2V2. So here was our initial molarity of magnesium and our initial volume, and then this is our final volume, and then we solve for M2, and notice we get the same answer, okay? But let's look at the nitrate. We gotta be careful, okay? Remember the initial molarity of the nitrate wasn't 0.75. That was the initial molarity of aluminum nitrate. The nitrate would be triple that, okay? So when you plug in M1 for the nitrate, you're not plugging in 0.75, you're plugging in 2.25. And if you recall, if we go all the way back to the top, remember when we were first mapping this out, I told you to make a note of the individual molarities of the ions, okay? So you really want to focus on that, okay? So if you do M1V1 equals M2V2 and you just accidentally put in 0.75 for the nitrate, then you would end up getting that question wrong, right? So the nitrate's initial molarity was 2.25, initial volume 50, final volume 100 milliliters, solve for M2. And notice when you do M1V1 equals M2V2, as long as your units of volume are the same, then it's just a ratio, so you don't need to convert to liters like we did in these calculations, okay? All right, so that's the shortcut for the spectator ions, okay? Now let's get to the more difficult question. What's the molarity of the aluminum ions? And the reason why we can't just do M1V1 equals M2V2 like we did with the spectator ions is because the moles we finish with that are dissolved are not equal to the moles we started with, because some of that aluminum, remember, precipitated out of solution, and now it's in the solid. So what we have to do is figure out how much aluminum is left over, right? So we started with an amount of aluminum that was dissolved, and we need to determine how much we lost to the precipitate, and if we subtract, that'll tell us how many moles of aluminum we have left dissolved. And once we figure out the moles of aluminum left dissolved, to get the molarity, we divide by the volume, right? Okay, so you gotta do 2 things. First, determine the initial moles of aluminum. So our source of aluminum in this reaction was aluminum nitrate. So if we do 0.05 liters times molarity gives us moles of aluminum nitrate, and it's a 1-to-1 ratio of aluminum to aluminum nitrate. So that gives us our initial moles of aluminum. So that's how many moles of aluminum ions I had dissolved to begin with, okay? But remember, because aluminum, some of the aluminum is in the precipitate, that's not how much I end with, right? So now we have to figure out how much aluminum actually dissolved, or actually precipitated, okay? And there's 2 ways to go about that, okay? Remember, we know 2 things. We know that the magnesium hydroxide is limiting, so this setup right here would tell me how many moles of aluminum react with the given amount of the limiting reactant. So I did liters times molarity of the limiting reactant. The ratio of excess reactant to limited reactant was 2 to 3, and then 1 mole of aluminum for every 1 mole of aluminum nitrate. So this setup will tell me how many moles of aluminum ions react with this much hydroxide, essentially. Or the other way to go about it is, remember, we've calculated how many grams of precipitate we have. So this setup would give us how many moles of aluminum are in this much of the precipitate. Now, when you do these calculations, they should come out to be the same number. With a little bit of rounding differences, it might not be exactly the same. I think when you do it this way, it comes out to be 0.025, and when you do it this way, it comes out to be 0.0249. So close enough, okay? So both these calculations give you the same amount, okay, 0.025 moles of aluminum, okay? So that's how many moles of aluminum were used in the reaction, were lost to the precipitate, okay? So to figure out what's left over, we take the moles of aluminum we started with, subtract the moles that precipitated out, and that equals the moles left dissolved. And to get the molarity of the moles left dissolved, all we have to do is divide by the volume. And it's the same volume for all the ions now because everything's in one container, taking up 100 milliliters, right? And so we get our molarity of the aluminum ions, okay? All right, so that was just a quick lesson on solution stoichiometry. That's probably, that type of problem, going through all that stuff, you're not always going to be asked every little detail of the question, but all of those details are probably important to know because you'll be asked questions about those details randomly. Okay, so again, I'll have another solution stoichiometry practice lesson posted probably sometime early next week, and that will be, instead of formation of a precipitate, it'll be when we do a double replacement reaction, and instead of losing ions to a precipitate, we're going to lose ions to a gas. A gas is going to be formed and it's going to bubble out of solution, and some of those ions, the amount of some of those ions in the reaction will go down. So it'll be very similar type of calculation, but instead of losing ions to a precipitate, we're going to lose ions to a gas. But to calculate everything is basically the same way. Okay, so again, that handout that I was kind of scrolling through as we did the practice will be posted with this video. The more practice you get with this stuff, the better off you're going to be. All right.